So here is the metric. It's super easy algebra. The difficulty is getting all the numbers for this, and we've explored that already, right? With counting carbon and counting money. So the metric sine qua non, without equal for carbon analysis is what is the marginal difference in cost for a carbon abatement project, and how much CO2 is avoided. And so it's dollars per metric ton. US dollars, metric ton, so 1,000 kilograms. And it's how much does the project cost minus the baseline. So, for example, buying a new car, the project would be an electric car versus a standard car. And you probably want the same features. You want it to fit 4 people. You want it to go 300 miles, blah, blah, blah. You can make that really stupid and just say, like, what's the upfront cost minus the upfront cost? Or you can be much more sophisticated, like we've saw on Tuesday, and say, well, what would be the annualized costs? What are my operation costs? All these different things. And that's going to give you much more confidence, and the consultant firm or corporation or academic paper you're writing much more confidence. On the denominator is the CO2 emissions of the baseline minus the CO2 emissions of the project. So notice, like, the sign convention changed here. We do project minus baseline because we're seeing how much it costs to make this change. And then we do baseline minus project on the CO2 because we're trying to see how much CO2 we avoided. There's no real point to do this if the signs were reversed, right? If your idea to reduce carbon actually emitted more carbon than baseline. So project minus baseline for money, baseline minus project for CO2. Keep track of that. And so we have to calculate all these things, right? We have to calculate the annualized cost for the project, annualized cost for the baseline, annual CO2 emissions for baseline, annual CO2 emissions for project. Sometimes this gets easy. Some people just assume if it's a renewable energy, like switching to solar, you just put 0 here. Baseline reductions for efficiency measures minus project is just going to be however much energy you save from that efficiency measure multiplied by the carbon intensity of whatever fuel that energy service was burning. So the CO2 side of it, I think, is a little easier to navigate than the dollar side of it, but we'll get into that. Okay. So swapping out old and incandescent light bulbs. This will be a pretty simple analysis. I can't even remember if I annualized this with a CRF or not, but this will give you kind of the first idea. So here's an old incandescent light bulb. Costs $1 per bulb. They last a year, burn 60 watts. When you have it on. Here's an LED light bulb. It's twice as expensive, $2 per light bulb, but it lasts 5 years. And so the annualized cost without getting into discount rates is 40 cents per year. So I assumed a 0% discount rate, right? So I just said $2 divided by 5 is 40 cents per year. $2 divided by 5 years is 40 cents per year. And it burns 10 watts to operate. Here are some assumptions that we know about that we have to employ to do this analysis. I assume that it's 10 cents per kilowatt hour. That's pretty typical of like Washington, Oregon, California. The power grid is basically natural gas, and so I assumed 500 grams per kilowatt hour, or 0.5 kilograms CO2 per kilowatt hour. And I assumed that we use the light bulb, about 15% of the year, so 1,000 hours per year. So here we go. Here's the marginal abatement cost, dollars per metric ton, project minus baseline. So the project is the LED, that's the carbon reduction measure. The baseline is the business as usual using an old light bulb. So here it all is. Here's the annual costs, or the annualized costs of the project 40 cents per year minus baseline $1 per year plus the difference in operational costs. So this is still project minus baseline. And so let's start with the power over here. Let me change my pointer. So here's 10 watts for the project minus 60 watts for the baseline. And since they operate the same amount of time per year, we can do power times time equals energy. So the difference in power, this delta in power times 1,000 hours, means that essentially now we're using this, we have 50 less kilowatt hours, right? And then we multiply that by the price of kilowatt hours, $0.1 per kilowatt hour. I should have done this stepwise instead of jumping right to the answer, but you can verify the math is correct or not. On the denominator, we have the carbon intensity of the fuel. The fuel is electricity, so 500 grams per kilowatt hour. We have to convert that to metric tons, because that's the units that the marginal abatement cost is always put in. And so here's 0.5 kilograms. There's 1 metric ton has 1,000 kilograms, so that's just a simple conversion there. And then this carbon intensity is multiplied by the amount of energy that we use, which is going to be the exact same equation as above, but now we are doing baseline minus project, because we're trying to see how much carbon we're avoiding. So we used to burn 60 watts times 1,000 hours times this carbon intensity, but now we're only burning 10 watts times 1,000 hours times this carbon intensity. And so there's that delta down here. And so it turns out this saves $221 per metric ton of CO2. Now, at first glance, you're like, what? If I switch my light bulb, I save $221 per year? No, absolutely not, because you're not burning that much energy, right? But if enough people switch their light bulbs out, then it would be $221 per year. If enough people switch it out to equal that metric ton down there. So what this is saying is that this switch will change you money. If you want to calculate exactly how much money it'll save you, well, then you do just this equation up here, right?
So would this change based off of how clean your grid is?
Yep.
Okay.
Yeah, so that's why towards the beginning, excellent question. So towards the beginning of this lecture, we had that three-legged stool, energy efficiency, which this would be, and then electrification, that doesn't matter because this is already electrified. And then that third stool is clean up your electricity. And so what's interesting, as the electricity grid gets cleaner, this denominator is going to get smaller and smaller and smaller. And so this number will, I suppose it'll get bigger and bigger. The marginal abatement cost gets kind of confusing when it's negative, especially when it gets really close to a very small abatement of CO2, because that means the denominator goes towards zero, and so the result will go towards infinity. And so that's why it's really important also to look at how many emissions are actually avoided. So there's this marginal abatement cost, and then we also look at total emissions avoided for a particular measure. Something could be like, nearly infinitely profitable to reduce the CO2, but the amount of CO2 it could reduce might be infinitely small. And so the actual resource pool, the actual ability to make money by reducing CO2 that way is near zero as well, because anything times zero is zero. So it's important to look at both.
Charlie?
Yeah.
So if the grid was dirtier, would that make you said $221 per megaton? Would that make that dollar amount bigger or smaller?
It would make this result smaller.
Okay.
Yeah.
So it would be less expensive to. Okay, yeah, that makes sense. Thank you.
Yeah. I get confused whenever this thing goes negative, and everybody else does too, even the experts that invented this kind of stuff, like Joel Swisher. And I asked him what happens, and he's like, yeah, the math becomes a little perverse. And he says it's because, you have a ratio of two subtractions. And he said, the point is, if it's negative, just do it, right? You're making money to save carbon. He said, so don't get too hung up on how negative it gets, just make the change. Which is kind of unsatisfactory to me because I want, beauty in mathematics or whatever. But it certainly works on the other side. If this is a positive number, then the more positive it is, the less attractive a mitigation strategy is. And that's also why it's important to actually see how much carbon is reduced. So we could do that math here. Where's my screen? Share screen. Let's grab this. So I just opened up R because it's a free calculator, right? So how much carbon does this actually reduce for just one single light bulb per year? So we do 0.5 kilograms per kilowatt hour. Times 1,000 hours times the power differential, which is 0.05 kilowatts, then divided by 1,000 to convert to metric tons. And so switching one light bulb avoids 25 kilograms CO2 per year. And so to actually get to that metric ton avoidance, it'd be 1,000 divided by 0.025. We need 40,000 light bulbs or something. That doesn't seem right. $25 times what? Guess that is right. Yeah. Yeah, so we need a lot of houses to be involved to do this. No, that isn't right. 1,000 divided by 25. We need 40 light bulbs to get a metric ton. All right. Hopefully that didn't cause more confusion, but what I'm trying to say is that we can calculate how much CO2 we actually avoid per light bulb, and then think about how many light bulbs we need to switch out to achieve a metric ton of avoided emissions over the course of a year. All right, I'm going to switch back. One of my daughters lost her pants. Common story in this household. Okay. All right, so that was the simple example. Let's get into more detail. So the mathematics of the actual equation, again, are simple, but it can take many forms, and the data collection can be super challenging. Some general forms include capital projects. So that's, building a different power plant that may produce less carbon. Replacement projects, so that'd be like swapping out a water heater that broke. Efficiency, so cost of saved energy projects. So that would be like swapping out light bulbs or insulating a house, or just changing your behavior, turning off lights when you leave rooms, or buying one of those Nest thermostats, a learning thermostat, Ecobee, Nest, etc. Fuel switching, this is like swapping out a coal-fired powered plant for a gas-fired power plant. Or switching from burning natural gas in your home to switching to electricity. The most important thing with all this is just be very clear with all your data sources and your methods so that the reader knows what you actually calculated and can make a honest comparison to something else. It's basic, good science practices. So what do you need to calculate a marginal abatement cost? You need a forecast of the stock of residential, commercial, transportation, and waste sectors specific to the calculation. So this is if you're doing it for a city or a nation. Basically, you need to know how big the market is. How many cars are in Bellingham? So if we switch all the cars to EVs, what would happen? So it's kind of these population calculations. You need to know the energy sources and their associated emission factors and efficiencies. So, what energy is being used for whatever project or baseline you're exploring. What is their carbon intensity? What is the efficiency of their power plants? Those sort of things. What are the line losses in the power distribution, electricity grid? What are the emission intensities of electrical grid mix? This is going to change from region to region and over time. Right now it's coming up on noon, so the emission intensity of grids all over the West Coast are quite low because of all solar power production. But come 6 p.m., it's going to skyrocket as the sun goes down and natural gas turbines fire up. Fuel prices can change. Prices for electricity can change. You should use a good approximation. Usually just going with today is a good guess, but you can also use informed estimations. Capital costs and reference technologies, both baseline and project. Just look it up. How much does a water heater cost on Home Depot, or how much does a car cost with Kelley Blue Book, or call a dealership, whatever. Operation and maintenance costs. These can be trickier to find out. The operation usually just depends on the fuel burn and then the price of the fuel. Maintenance, you usually need to ask a company, to have a look at their books to see what actually happens there. Lifetime of the technologies is really important. That's what you use to actually annualize the cost of something. So if a project lasts a different amount of time than baseline, then that loan term is going to change, right? The last thing you want to do is continue to pay a loan for something that's already broken. Discount or interest rates. So this can change depending on whether it's a corporation that could be investing their capital and get like a 10% return versus a city which runs off municipal bonds, which are about 5%, versus a household which usually dials their interest rates to like a mortgage payment, which is like 3 to 4%. Or even there could be really painful examples too, like a developing nation with unstable economies or unstable currencies, and then you'd have a super steep discount rate of like 20%. Maybe that money should have been spent for better healthcare rather than carbon avoidance, and so the discount rate will change. You also have to understand something called a no action alternative, and so that's the cost of doing nothing. Maybe sometimes that can even be more expensive than doing something, right? You can think of many examples, like the cost of not getting enough exercise per week is going to be more expensive over the course of your life than if you choose to exercise every once in a while. And so thinking about these no action alternatives can be subjective and tricky, but it's important. I think one of the ones I had the most struggle thinking about was what's the no action alternative cost of not making Railroad Avenue walkable. Like, we could think of, it's difficult to think like how that changes the economies of that particular street. What's the cost of doing nothing? How much money do we save or gain by doing something? How much carbon is avoided? Okay, so let's go into a detailed example. I lost the chat again. Okay. So residential water heaters. So the baseline, what people typically do in Bellingham is they go buy a high efficiency gas water heater. They've been told to do that since the 80s or so that, gas is cheaper than electricity. So go buy a gas water heater. Holds 50 gallons, so kind of standard for a family of 4 or something. Has an efficiency of 0.68, 68%. So when we burn that natural gas, 32% of that heat energy goes out the stack. And that's just second law of thermo. Can't avoid that. It costs $1,000 and $1,059, and I put a link down here to the page on Home Depot where you can buy it today. And it's warranted for 6 years, and here's a picture of it. Pretty cool. Now here's the alternative. This is the project. It's a hybrid heat pump electric water heater. Same size, 50 gallons, so it provides the same energy service to that family. That's pretty important when you're making these comparisons. You want to make sure that it still does what you want it to do. It has an efficiency of 355%. That's because it's not generating all the heat for the water. It's moving that heat using a heat pump. It steals heat from outside or from your basement and operates a refrigeration cycle and deposits cold air into the environment and heat into the water. It's more expensive. It's fancier, so it costs $1,300 up front. It used to actually be less expensive. It used to be $800 because PSE had a rebate going all for the last 2 years, but then as of January this year, they quietly canceled it. This was even before the economic destruction. This also was the first year that PSE has become a natural gas corporation rather than an electricity corporation. They generate more revenue from selling natural gas than they do electricity. And for that reason, why would they want to pay you to use electricity? They want you to use natural gas. I'm being cynical, but I can't understand any other reason why they got rid of that rebate. Many other power companies provide a rebate for natural gas. I mean, for electric heat pump water heaters. So like PG&E down in California, Jefferson PUD, Snohomish PUD, Seattle City Light, they all still provide big rebates. But I've digressed into cynicism and politics. So point is, this one's more expensive. It's $1,300. It lasts longer though. It lasts 10 years. It's warranted for 10 years. Natural gas heaters don't last as long because that constant burning of natural gas underneath a hot plate or a hot coil causes mineral deposits from the water, and eventually those deposits get so thick that it's not very efficient at all anymore, and you need to replace it. General facts and assumptions for this analysis: 5% discount rate, electric price 9 cents per kilowatt hour, gas price $1 per therm, water temperature in. So we need to figure out how much energy we actually need, right? And so we have to use Energy 101 or Energy 380 calculation, namely the heat capacity equation, right? Change of energy equals mass times heat capacity times change in temperature. So what's the change in temperature? Well, the water comes into the water heater at 55 degrees Fahrenheit. The water comes out at 120 degrees Fahrenheit. We use 55 gallons of water per day in a household. And then now we need to calculate the amount of energy. So we use that heat capacity equation. I'm doing it in American units because they're actually kind of easy for this kind of analysis. And so water density is 8.34 pounds per gallon. So now we can figure out how many pounds of water we have. So we can do that mass times heat capacity times delta T. The heat capacity of water in American units is actually kind of elegant. It's just 1 BTU, because that's how a BTU is defined. 1 BTU per pound of water per degree Fahrenheit of temperature change. Therm has 1,000 BTUs. That way we can backcast to how many therms we use. And a BTU, or a kilowatt hour, has 3,412 BTUs. I want it to be like 3,600 because that way it's like, a kilowatt hour, 3.6 times 10 to the 6 joules. but it's off a little bit. It doesn't get all the way up to 36 because a BTU is actually 1,055 joules instead of 1,000 joules. Okay, so here's all the assumptions and facts we need for this. And we also need the carbon dioxide intensities. So this is more for counting coin. Now we got to count carbon. I guess we still need this heat capacity equation for the carbon side. So PSE internal report has a carbon intensity of 0.47 kilograms CO2 per kilowatt hour. This is similar to natural gas. PSE's blend back in 2018 was natural gas, hydro, and coal. Hydro plus coal kind of averages to natural gas, right? 1,000 plus nearly zero is about 500. Natural gas is about 500. All right, so gas carbon intensity is just from EIA.gov. It's 5.31 kilograms CO2 per therm. So if you burn a therm of gas, if you burn 100,000 BTUs of gas, you pump 5.31 kilograms CO2 into the atmosphere. Recent studies, Alvarez et al. In Science, says that America has a leakage rate of 2.8%. And so this definitely will make the natural gas look a lot worse, especially if we assume, global warming potential of like 28 on a 100-year time horizon. I didn't do that in this analysis because, spoiler alert, the electric heat pump already wins, so I don't even need to use methane leakage to show that this is a better option than natural gas. 1 therm of methane is 1.92 kilograms. So if you actually wanted to use this leakage rate, then you could multiply how many therms we use by that leakage rate, which isn't quite right. We'll get into that in later lectures, and then multiply it by this global warming potential value. All right, so that was a lot. Just trying to set up the problem.
I have a really quick question.
Yeah.
What do they use for it's kind of a little off topic but for weight of natural gas, what's the standard pressure to get that weight? If that makes sense. Or is that just
I understand your question, and it's difficult to so the pressure of the gas in your lines, it's low because you don't want it to be crazy. I think it's just I don't know. I'm not even going to pretend to know. Okay. So I struggle with all this stuff too, like trying to figure out, what's, a therm in terms of volume. A therm is a 100 cubic feet. And I don't know what I think that's at STP actually, not the pressure of your line. Yeah. 100 cubic feet at STP, which is 25 degrees Celsius or 20 C in 1 atmosphere is a therm. But you don't even need to know the pressure to get to the mass of the gas.
Yeah, I guess I didn't really think about that, how there's just the methane will have a physical weight. Yeah.
And that's because, methane weighs 12 grams per mole for the carbon, 4 grams per mole for the 4 hydrogen. So methane weighs 16 grams per mole, and it has a change in enthalpy of negative 890 kilojoules per kilogram or something. I don't know. You can look that up. I think I talked about it on the second lecture. And so from those two facts, you can convert the kilojoules to therms, and then you can calculate how much methane you need, and then you get that result. 1 therm of methane is 1.92 kilograms. Let me see if I did any of that stuff. I've been doing some calculations on the side. Yeah. How do I get this screen on me? Full screen. I don't know. This is pretty janky. That's not gonna work. I'll just list the facts. The change in enthalpy from natural gas is 890.3 kilojoules per mole. And we know that natural gas weighs 16 grams per mole. And so therefore we can get that result from here. We can calculate how many moles are in a therm, and then calculate how much that would weigh. And the result will be 1 therm of methane is 1.92 kilograms.
Yeah, and then I guess to add on to that, like the natural gas that I'm getting, like to my house or something, like that's not purely methane, right? Like there's got to be some other stuff hanging out.
Yeah, I forget, it's something like 95% methane. It also has some CO in it, carbon monoxide, and that's still burnable, right? You can burn carbon monoxide with oxygen and make CO2. And it has a trace amount of hydrogen sometimes. It can have water in it. It can have whatever C2 is. Is that butane? And ethane, some slightly higher hydrocarbons as well. Yeah, you can look at what the gas mix. You can get a better idea what the gas mix is by looking at your gas bill, and it has something called the energy correction factor, and it's something usually slightly above 1, and it's saying that this isn't pure methane. It actually gives you slightly more energy than pure methane, and that's usually because it has a few higher chain hydrocarbons in it that are still gaseous, like ethane and butane and that sort of stuff. Hopefully that helps.
Yeah, it does.
Okay, so this is gonna get gnarly. I should have animated this slide, but when you add pretty PDFs like this into PowerPoint, it crashes. So I just wanted to make sure it didn't crash, so I put it all on at once. All right, so there's many places to begin, because recall there's 4 different values we're trying to calculate. So you can kind of choose your own adventure, but that's why bookkeeping is so important. So I'm going to start with the costs of the fuel costs, right? So let's start with electricity. We use this water heater 365 days. We use 55 gallons per day. So this gives us total amount of gallons we use per year, but we need mass. And so we multiply it by the mass per gallon, 8.34. But we truly need energy, not mass. And so now we multiply it by the heat capacity equation. So we know that there's 1 BTU of energy required for every pound, and for every degree Fahrenheit we change the water temperature, and we're changing that water temperature by 120 minus 55 degrees Fahrenheit. So this is heat capacity equation multiplied by mass. And then we need it in kilowatt hours, not BTUs, and so we convert to kilowatt hours with these equations here. So we end up with 898 kilowatt hours. And to get to money, we multiply by the price per kilowatt hour is 9 cents per kilowatt hour is 80.8. Trying to figure out what this 3.55 is. What did I do there?
Looks like it's the efficiency of the heat pump.
Oh yeah, thank you. Yeah, it's like I didn't label it. It doesn't have units, and that's because efficiency doesn't have units. Yeah, thank you. So we don't actually need all that energy because we're not heating up all this water. We are moving heat from our basement or from the outside, and so the total amount of energy is reduced by this excellent efficiency of the electric heat pump. Yeah, so the total amount of energy required is 898 kilowatt hours. At 9 cents a kilowatt hour is $80.08 per year to operate. How much CO2 do we emit? Well, that's the energy multiplied by the carbon intensity of that energy. So 898 kilowatt hours of energy multiplied by 0.4726 kilograms per kilowatt hour carbon intensity. Converting that to metric tons with 1 over 1,000, and we emit about a half metric ton of carbon dioxide per year with that heat pump water heater. Similar analysis with the gas water heater. Number of days we need it, that's all year long. Number of gallons we need to heat per day. Mass per unit gallon heat capacity equation is identical. We still want it at 120 degrees, and it's still coming in at 55. Efficiency is very different. So that efficiency above 1 for the hybrid water heater decreased the amount of energy we needed. This poor efficiency actually increases the amount of energy we needed, because not all the energy that you burn in the gas water heater is going to heat the water. Some of it's going up the smokestack. So this 1.068 causes us to grow, and we convert the number of BTUs we calculate from the heat capacity equation to therms, so we can match it to our power bill. We see that we require 160,000 therms of natural gas to power that natural gas water heater, and at $1 per therm, it's $160. So it's twice as expensive to use each year. And that's all because it's this factor of 5x difference in efficiency. I presented this analysis and to the city of Bellingham, and you always get all these comments from the public. I don't think I'm ever going to be involved in politics again. And somebody emailed to me, and he said, I'm a retired engineer, and your analysis is insane. You assume that the efficiency of the electric, based on your analysis, you'd have to have an efficiency of your electric water heater that's 5 times greater than the gas water heater. And so I emailed him these 2 links to the Home Depot website, and I said 3.55 divided by 0.68 is actually much greater than 5x. It's closer to 6x. I go, are we done here? And then he didn't reply. I don't know what the moral of that story is. Check your math before you sound off.
Yeah.
Okay. How much CO2 is produced? 160 therms multiplied by the carbon intensity of that energy, 5.307 kilograms per therm, converting to metric tons, and it produces 850 metric tons of CO2. So it's again about twice X. So you can already see where this is going to go. The delta CO2 is CO2 baseline minus project, because we're trying to see how much CO2 we're saving. So we used to emit this much CO2, now we'll emit this much CO2. So 0.849 minus 0.424 equals 0.425 metric tons of CO2. If we did want to assume this methane leakage, let's actually just get to the answer and then we'll go to the methane stuff. So we did the carbon analysis here, 0.525. We got the delta CO2. Now we need the delta dollars. We have the operating costs already, 160 per year for the gas, 80 per year for the electricity. But now we have to look at the capital costs, and we're going to annualize those. So while the electric heat pump lasts 10 years, the gas water heater only lasts 6 years. These different lifetimes mean different cost recovery factor values and different annualized costs. So not only will the costs be different because they cost differently, the heat pump, it's like $300 more than the gas one, but they last different amounts of time. So their annualized costs are going to change. So here again is that cost recovery factor equation. You can also use that payment function in Excel. D is the discount rate or interest rate, and N is the number of years the loan exists. And in these analysis, we peg the number of years the loan exists to the lifetime of the project, because you're basically saying, how much do I have to pay per year to use this thing? So at 5% interest rate and 6 years, so this is for the gas one, right? Because we're at 6 years, not 10 years. Cost recovery factor of 0.2 per year. So the annualized cost will be the capital cost, 1,059, multiplied by, that's the wrong cost recovery factor. But I did do 0.2 actually here. So ignore this. This answer is right for 0.2, but I've typed the wrong thing here. Do you guys understand? Forgive me? Cool? Good. All right, so this should say 0.2, and if it did say 0.2, we'd get this result. So the answer is correct, just the setup of this equation is wrong. Okay, so this natural gas water heater annualized over 6 years costs us $208 per year. The total costs are going to be those annual costs plus the operational costs. 208 plus 160 equals $368 per year. So that's for the gas. Now let's do it for the electric heat pump water heater. It has a cost recovery factor that's different because the interest rate's the same, but the lifetime is different. So it lasts 10 years, not 6 years. And so its cost recovery factor is 0.3 per year. It's lower because we have more time to pay it off. We have 10 years to pay it off, not 6 years to pay it off. So the annualized cost will be the capital cost, $1,300, multiplied by 0.13. That's the CRF, cost recovery factor. You get an annualized cost of $168.36 per year. The total cost would be that annualized capital plus the operational, and so it costs $248 per year. So this is cheaper.
What is the Y standing for again?
Years to the per
Okay.
year.
Sweet.
Y to the -1, yeah. Yeah, so sometimes I do it this way, sometimes I do it this way.
Did you
And
get
sometimes I call it year and sometimes I call it Y. I don't know.
is the 80 like the operational cost, the $80 and the 160? Did you just look that up?
No, we calculated that on the last slide. So
Oh,
we calculated how much mass of water we needed, how much temperature we needed to change it. That tells us how much energy we need per year. We multiply that amount of energy by that cost of the energy, and we get $80 for the electricity. We need even more energy for the gas because it's less efficient, and so we need 160 therms multiplied by $1 a therm. It's $160 for the gas.
okay, gotcha.
If they had the same efficiency, gas would actually be cheaper because a therm is much cheaper per unit energy than a kilowatt hour. The problem with gas is it's terribly inefficient because you're just burning stuff, and so you actually have to use a lot more energy to get the same amount of thing. Remember that energy ladder in 380 or 101? The quality of gas isn't nearly as good as the quality of electricity. And it's not even the gas. If we could actually use a fuel cell, we'd get a lot more energy out of that gas because we'd be going from chemistry to heat. But instead, we burn it, so we're going from heat to heat, which is kind of straight across on energy quality. Whereas this way, we're going from electricity to heat, which is much down the energy quality ladder. So we get to benefit from that with this tremendous efficiency. All right, so those annualized capital costs are here and here for gas and electricity, respectively. So even though the natural gas water heater capital cost is less, right? It's $1,059. Its annualized costs are more because it only lasts 6 years. After 6 years, you got to buy another one for $1,059. And so that's what's so cool about this cost recovery factor is it captures that. It captures that lifetime. So things that last longer cost less over time. It's like Terry Pratchett's boot theory of economics. He's a fiction writer, right? And I forget which book he wrote about this in. I read it a long time ago when I was a kid. But it basically said that a rich man pays less for boots over time because a rich man can buy a pair of boots for $100 that'll last 5 years, and a poor man buys a pair of boots for $50, but they only last 2 years. And so over time, the rich man saves $100 every 5 years or so compared to the poor man. And so things that last longer cost less money over time. And you can figure that out with this cost recovery factor. You can also make the decision based on your own personal interest rate or discount rate what the break-even point is. Where does it make sense to actually buy the cheaper thing rather than the more expensive thing? So I'm just digressing here, but with tools, every once in a while I'm like, okay, I need this funny little screwdriver or wrench to do some project around my house or fix something on my car. And so my philosophy, I buy a real shitty one from Harbor Freight or whatever and see how long it lasts. If that one breaks, if my crappy tool breaks, then I go to Hardware Sales and get the fancy version because I assume okay, I need to use this again and again over time. But if it's just a one-off thing, I'll just buy the crummy one and see how long it lasts. You can geek out on this stuff.
Earlier, it's the CRF for the first one is 1059 times 0.2, correct?
Yes.
And that doesn't equal 208.64.
It does not?
It does not.
What does it equal?
To 11.8.
Okay.
So like close-ish.
Close-ish, and at least it didn't change the result too much. Natural gas still looks bad, but
Yeah.
thank you. So I need to fix this slide, and I'll change it.
I mean, it might be that like you were using more decimal points because the next one is also slightly off. But that's
Oh.
just supposed to be 169 if you use 0.13.
Oh yeah, I was using way more decimal points because I was just using R, which goes.
Oh, okay.
But okay, so what happens if you do it by 0.13? Then it'd be like 100 and something. So this
It's,
result is right within
Yeah.
significant figures.
Yeah.
But this
close-ish.
result is right. But this thing is wrong. So I only need to change the 0.3. And people should be pretty happy. I'm happy anyways. All right, where was I going with this? So the annual cost for the electricity is 168 plus 80. So now we can actually do the calculate the marginal abatement cost, right? Dollars per metric ton. So it's dollar project minus dollar baseline over CO2 baseline minus CO2 project. So the electricity is 248 annualized. So that's annualized capital costs plus operational costs minus the baseline for the gas, annualized costs plus operational costs. And then the difference in baseline emissions, 0.849 metric tons minus God damn it. The baseline emissions, 0.849 metric tons minus the project emissions, 0.24 metric tons. And so we get a negative $120 per year, meaning we save $120 per year to make this switch. And we also reduced our emissions by 0.425 metric tons per year. And so the marginal abatement cost for this reduction strategy is negative $282 per metric ton. So the household saves $120 per year, but on a per metric ton basis, it's negative $282 per year. So that's also kind of saying like, well, this is how much I'd save if I did it for 2 years or so, 2 years and some change, or if 2 households did this. We'd collectively reduce a metric ton of CO2 and collectively save $282. All right, so not only does the electric heat pump water heater reduce emissions, but it saves money for which 2 reasons? What are the 2 reasons the heat pump saves money in carbon?
It's
Is it-
more energy efficient.
Yep, that's the most obvious one.
Someone in the chat says it lasts longer.
Lasts longer. Oh, that's a 3rd reason actually. Think about the second part of this question. How could the heat pump reduce emissions further?
Is it because the grid could be
There
run
you
by
go.
renewable electricity?
Yeah, you got it, Morgan. So clean up the grid, the heat pump only gets better with time. Natural gas is just going to stay the same level of suck forever. And so that's why these 3 things, energy efficiency, decarbonizing the grid, and getting rid of scope 1 emissions, they all work together and they all make things better and better and better in time. And that was the idea behind Elon Musk's entire business model. Let's electrify transportation with Tesla, and then let's clean up the grid with Solar City or whatever. He's just kind of like 20, 30 years too soon, but I'm happy he gave it a shot, and we're all learning from his activities. All right, so that was a detailed example of calculating marginal abatement cost for just simply switching a water heater. You can see why, this took an entire lecture. You can see why trying to figure out something like for a city or a corporation, like what if Amazon had their delivery service on track or something janky like that? let's have Amazon switch out all the on-track delivery vans to electricity. What would be the cost of that? What would be the avoided emissions? That would be a calculation that will take, months versus this one that took a day.
I'm confused about how this is a curve.
Did I say the word curve yet? Kept on calling it the marginal abatement cost, but then the marginal abatement cost curve. Oh, at the very beginning. So you build up the curve by starting to piece together several different strategies. So this was just one strategy, and it will have a dollar per metric ton, and then other strategies will have different dollars per metric tons. And then you order them from cheapest to most expensive, and it'll produce this curve, and you label each point with the mitigation strategy that you're looking at. So this was negative 282 per metric ton. The light bulb was negative 221 per ton. So this switching water heaters would be a little bit more more negative than the light bulb. So let's get into that. So here's a few example curves for a city and then for the world. And the city is for Toronto. So using the marginal abatement cost for any measure, we can now rank measures for a home or a city or a nation or even a world. This generates the MAC curve, the marginal abatement cost curve. And the standard way of displaying this is on the y-axis, you put that marginal abatement cost, dollars per metric ton CO2, and on the x-axis, you put cumulative abatement potential. So how many metric tons are actually avoided from a particular strategy. And to calculate that, you say, well, what's the avoidance of that strategy per year multiplied by the number of iterances you can apply that strategy to. So something like switching out Railroad Avenue to a walkable, you can only do that once. But something like water heaters, well, let's estimate how many gas water heaters are in the entire city of Bellingham and multiply that per water heater number, 0.425 metric tons per water heater, multiplied by total amount of water heaters, and then you'd get that cumulative CO2 avoidance for that mitigation strategy. And so that's what the x-axis of these different blocks are. So the cost determines the y-axis. How fat this abatement is determined by how much carbon you can actually avoid. So some things may be super cost effective, but you might not be able to even make a dent in the actual carbon budget. Other things could be expensive, but they could have a huge potential for reducing carbon. Something like carbon capture and sequestration. We could theoretically get rid of all the CO2 we're emitting per year by building massive carbon capture and sequestration facilities and solar panels to power them the world over. It'd just be stupid expensive, and that's not going to ever happen. Or similarly, we could do something like I can't think of like something that would be steeply negative but ineffective. Who knows? Let's look at some real curves. So this is for Toronto. Marginal abatement costs on the side, $2012 per metric ton CO2. And here is the abatement potential. You don't actually get to see how much CO2 is avoided per each measure. You'd have to kind of make a subtraction. So here's building nuclear power plants. It has a cost of about like $80 per metric ton CO2 avoided. So we'd have to spend money to build this power plant. Nuclear power plants are expensive because they're risky and you have to have crazy insurance for them. And how much CO2 could avoid, and this is by this chart I think is for 2050. So how much CO2 is avoided by 2050? No, this is 2020, it says right here. So this is how much CO2 we'd avoid by 2020. So if we built a nuclear power plant, it cost $80 per metric ton of CO2 avoided, but it would avoid 10 minus 6 megatons of CO2 So that's 1 million metric tons. So you can see why these charts are really great visually, because you can rank all the different marginal abatement cost strategies. So some of the negative ones are often efficiency, right? So let's change our refrigerator, change our lighting, change the way we heat water. Lighting with LEDs is more cost effective than lighting with compact fluorescents. There's all sorts of different things here. Natural gas water heater is not as, it's an efficiency thing, right? A tankless water heater uses far less energy than a standard natural gas water heater, because you're not keeping the water hot all the time. You just heat the water when you actually need it. But that's still not as good as a tanked electric heat pump water heater, and that's because of that huge efficiency gain. And that's not as good as a solar air water heater, because you just have to pay upfront capital costs for a solar water heater, and then it just heats water for free from the sun. It might not be as reliable, but it's the fuel source is free. Different things like that. The ones that are positive usually are things that are trying to generate cleaner electricity, and so that has pretty big upfront capital costs that can often be larger than the capital costs of dirtier fossil fuel plants. They don't have as much operational cost, but the capital costs can be expensive. There's like biogas, hydropower, nukes, wind, residential photovoltaics. They're the steepest. But this study was done back in 2016, and already that's changed significantly, as we saw in last lecture when we calculated some of this for my house.
I had a question about these graphs.
Yeah.
So do these include things that are like CO2 equivalents for like other gases that have a much higher global warming potential than CO2, obviously?
They absolutely should. This graph does not look like it did, because it just says CO2. It doesn't say CO2e. But they absolutely should. So I would expect that when you calculate this for this class. And for this class, the project, I don't want you to generate a whole curve. That'd be impossible. Just find one strategy, either for the city of Bellingham, for Huxley College of the Environment, or for COVID-19, and try to see how much CO2 was avoided and how much did it cost. And then if people do similar, if they have a similar overarching region like Huxley College of the Environment, then we could start bending some of them together and produce a small little graph for, say, Huxley College. But yes, absolutely, we should include any greenhouse gas. As we saw in that in the carbon accounting lecture, the sulfur hexafluoride used at the Stanford Linear Accelerator Laboratory is like almost equivalent to all of the emissions from the entire Stanford campus. And so yeah, not including other greenhouse gases is super foolish. Okay, and then here's one of the first ones to really make it big. Joel Swisher was making these back in the 90s, but I don't know, didn't make it out there. But everybody really geeked out on these back in 2013 when McKinsey released this curve for the entire world. And so it's the abatement cost here in euros per metric ton CO2, and this is abatement potential in gigatons of CO2 equivalent per year. Again, energy efficiency, usually deeply negative. Hybrid cars, electric cars hadn't really even taken off yet. And then they even include some land use strategies here. So soil restoration, grassland management, reduced pasture land conversion, reduce slash and burn. I don't know if they have silviculture or things like that. It'd be cool. So also look at the drawdown book, and you could also just pick one of those strategies and think about those. And I'll be very forgiving if you pick a strategy that's much more nebulous and difficult to constrain. I'd just be very interested in like your thinking and formulation of the problem. Whereas if you pick something very well constrained and easy to calculate, like let's switch out everybody's thermostat in Bellingham for a Nest thermostat, then I'll expect pretty detailed calculations, because that's something where you have all the assumptions and constraints available. And then again, some of the most expensive stuff is changing the way power generating is generated. And the most expensive stuff is all this carbon capture and sequestration. And that's because you're fighting thermodynamics, right? Like carbon absolutely loves to be attached to oxygen. And so trying to either shove that underground or break it back apart is going to be expensive energetically. And things that are expensive energetically are going to be expensive economically. All right, so that's the marginal abatement cost, the marginal abatement cost curve. So we put it all together. That's basically all we need to learn for this class. Now the trick is trying to figure out how to calculate some of these different things individually with all the nuances, and to better understand how these mitigation strategies work. So Tuesday, we don't have a lecture. We have the carbon hackathon. Thursday, we're going to work on homework. We'll have a work study session. And then next Tuesday, not the 21st or whatever, but the 28th, we'll start to look at buildings. So what are the mitigation strategies for buildings? So changing out lighting, changing out heating and cooling, those sorts of things. And then the week after that, I think we're doing transportation, so we can look at like EVs versus standard. And the week after that, I think we're looking at electricity generation things. And then it's going to get really nebulous. We start to get into like land use and stuff like that. And I don't know anything about that stuff. So we'll just kind of hold discussions about it. And then the last couple weeks of the class, we'll just be working on our projects. Sound good?
I have a few questions about the homework.
Yeah, let's get into it.
My first question is under the assumption that it says, assuming that San Pellegrino comes from Italy and it travels like all these miles, and then at the end it goes, making one trip for every 2 cases of water. Is that one trip for every 2 cases of water for all modes of transportation or just the Volvo?
That's just the Volvo. Yeah, sorry, that wasn't very clear.
That's okay. And then I didn't see a miles per gallon for the Volvo or like the fuel intensity for that.
Yeah. Yeah, I didn't put that in there. That's just something you can guess.
Okay.
Yeah, so
So we can,
I try to put some kind of real world things in these background data. So I try to leave out something that you have to figure out for yourself or make a good guess. And then I often put too much information in, because that's actually one of the harder problems with like a consultantship gig, is they throw way too much information at you and a lot of it's useless. So you have to like decide which is superfluous. So for example, in this problem, I put what did I do? Empty spring bottles weigh 1.5 kilograms. Now, the mass of the San Pellegrino definitely matters because it's being shipped across the world. So you have to look at, ton miles, short ton miles, right? Like you have to spend energy to move mass on a ship. Now, this empty spring bottle weighs 1.5 kilograms, but it's not going in a ship or a truck. It's just going in the Volvo. And do you think that 1.5 kilogram makes any difference whatsoever?
No.
The Volvo is going to burn the same amount of gasoline. Maybe if you put in, several other people, like 4 people, then you got it up to 150 kilograms, it'd make a difference in your gas mileage slightly. But this water bottle, this mass doesn't matter at all.
You're just refilling the water. You're not like buying a spare one or
Yeah, so this
the
is
same.
empty
One
spring
point.
bottles weigh 1.5 kilograms and hold 39 liters of water. So it's one of those big, what are those called? I don't know. You know those big things you can fill up at a store? I don't actually do this, but I was trying to like make it be as fancy as San Pellegrino so people are getting like fancy water from somewhere. I see people down by Oyster Dome filling up water out of waterfalls and stuff. I don't know if that's smart or not. Other questions about the homework? You said you had a couple.
Yeah, and then I'm confused about like the canister. You're
I
like
just realized I'm not even sharing my screen anymore. Sorry.
it's okay.
Confused about the canister. Yeah.
Yeah, it like fills up. It like puts carbonation in the water, and then it also like the canister has 1 kilogram of CO2, and it like takes 1 kilogram to put it in there. So is for each canister, is that 2 kilograms? Like, are we assuming that the
Yeah.
okay?
So I'll go back to that first one since I realized I wasn't sharing my slide. So empty spring bottles weigh 1.5 kilograms. This information is superfluous because it doesn't affect the miles per gallon of the Volvo, and therefore the CO2 per mile of the Volvo. I didn't put the miles per gallon of the Volvo. You could just guess 20 or something, 25. Then your next question was each CO2 canister contains 1 kilogram of CO2. So it's charged with, pressurized with 1 kilogram of CO2. When you press that button and it charges your water into soda water, it uses a little bit. I forget how many times you can charge it. Oh yeah. One CO2 canister could charge 78 liters of water. But once you have charged 78 liters of water, you've expelled all the CO2 out of that canister. And so all that CO2 has now leaked into the atmosphere. Slowly, I guess, right? First it went into the water, and then it went into your belly, and then you burp it out or whatever. And so then all that 1 kilogram of CO2 in the canister now goes into the atmosphere. But that 1 kilogram of CO2 didn't come for free. It had scope 3 emissions. You had to not only fill it with 1 kilogram of CO2, but it cost energy to fill it up. And so the scope 3 emissions causes an additional 1 kilogram of CO2 emissions to produce, compress, and transport. So this is all like scope 3 emissions for that 1 kilogram of CO2 that's in the bottle. So each canister. So each canister actually produces 2 kilograms of CO2, not just the one that's inside of it. Savvy?
I have a separate question, a little unrelated, and I guess slightly off topic, but like, I don't know if you know this, but if you consume CO2, do you actually just release all of that back as CO2, or is there any loss?
Yeah, you release it all back. It's inert in your body.
Okay.
It's like eating a piece of sand.
For that extra, for the 1 kilogram of CO2 that's, I guess, like embodied in the canister,
Yeah, good word.
that 1 kilogram specifically, that gets, if you refill it, that'll get divided over the year by how many times you refill it, right? Because if you refill it, then that's like one.
Yeah, okay, good. So I did not include the embodied CO2 of making the steel canister. This is the embodied CO2 of the CO2. So when you go to the store to recharge your canister, they have a big canister that they charge your canister with, and that's what you have.
Oh,
And so that CO2 in the big canister at the store has the embodied, or not even that canister does. It's the CO2 in that canister has an embodied kilogram of CO2.
okay. So
CO2
that's
came
just
from somewhere, and it had to be compressed, and then it had to be moved from that plant to the grocery store.
Okay, so that 1 kilogram is just physically refilling it. It's not the production of the can itself.
Yeah, I didn't include that because I figured that'd be de minimis. Like, I guess you could look up the amount of kilograms of CO2 per kilogram of steel and
Okay.
divide that over how many times it's used for 5 years, but it's going to be pretty trivial.
Okay.
But good question.
After the lifetime of the machine, like 5 years, can't you like fix them and or just like take better care of them to make them last longer?
Totally.
So like
Yeah.
couldn't you extend that farther if you're
Yeah.
like pushing it?
Yeah, I mean, some of this stuff I just made up for the sake of learning about like cost recovery factory and stuff like that. But yeah, I'm sure it'll last longer than 5 years. And if it breaks, it's probably like a little plastic thing. You could just, glue a golf ball onto the top of it and it'd still work again. Who knows? I think we'll start learning about taking better care of our stuff now that the economy's collapsed worldwide. Cool. Depression era stuff. Yeah, my grandfather was born in the 20s, and so he kind of was like a teenager during the Great Depression, and then he went to like World War II and stuff. He like saved everything. Like if he took something apart, he'd save like all the screws and nails and have it in like different jars in his garage and stuff. It's insane. But we might have to start learning those lessons again. Anything else?
Charlie, I had a question.
Yeah.
So I just want to make sure like I'm thinking about this correctly. So like I found like the MPG of the Volvo, and I divided like the miles per trip by the miles per gallon to get the gallons per trip.
Yeah.
Okay, and then I divided like the 10 miles that's being driven, like so that you'd get the amount of gallons of gas per mile. And then I don't actually know if I needed to do that. And then I multiplied the gallons per mile by the metric tons of CO2 per gallon of gas.
Yeah, it sounds like you might need the total miles driven over the year in there somewhere.
Okay, that makes sense. But is that the right way to think about it though?
That's certainly, yeah, that is the right way to think about it. But there's different pathways, right? Because it's all just like unit conversion multiplied all against each other. Basically, you want to figure out how many gallons the Volvo uses per year, and then you can figure out how much CO2 happens per year. And to get how many gallons the Volvo uses per year, you have to think about how many miles it drives per year, and then it's miles per gallon. And to get how many miles it drives per year, you have to think about how many trips it makes per year and how far that trip is.
Okay, thank you.
Yeah. Are you in Hawaii or back in Bellingham, Ryan?
I'm stuck in Hawaii. My flight got canceled.
Yeah. Wow. All right. Well, let me know how I can help. Anything else? All right. I'll try to figure out this password thing on the videos. And if I can't, I'll just start posting stuff to YouTube. Is that you, Patrick? It's a crazy like chipmunk. It sounds like my girls are playing this game called Animal Crossing, and it sounds like how the raccoons talk. Maybe just type it in chat. I don't know what's going on.
Is that better?
Yes, that works.
Okay, I just switched my microphone.
Yeah.
Yeah, I can help you figure it out if you want.
Oh, the Zoom password thing?
Mm-hmm.
Okay.
'Cause I had to do the same thing.
Do you have, as a TA, do you have access to the cloud recordings on Canvas?
I don't know, but I do the cloud recordings for a different class.
Okay.
So I can show you how to turn off the password feature.
Okay, cool. All right. things. And I need to talk to you too about research at some point.
Yeah.
All right, I'll call you after this lecture on phone. Anything else about the homework? All right, let's call it a day. So we won't see each other on Zoom until a week from now, till Thursday. So have fun at the Carbon Hackathon from your house. And email me for homework questions and things like that. I'll be around. All right, adios.